Ну да. Начнем. Всем привет, нас сегодня немного. В общем, я хочу представить вам Дениса. Этот человек вообще из Днепропетровска, но сейчас, я не знаю, работает, учится, живет в Швейцарии, в EPFL. Я думаю, он еще расскажет о том, что это такое и, возможно, как он туда попал. В общем, давайте поприветствуем Дениса.
Раз, два, три. Окей. Всем привет. По поводу доклада есть две опции. Я могу попробовать говорить на ломаном русском вперемешку с английским или могу говорить по-английски. Я никогда не давал технические доклады по-русски, так что ваш выбор, я не знаю. На ломаном, отлично, хорошо, отлично. Да ладно. Английский, хорошо. Okay. So my name is Dennis. I work/study at EPFL. EPFL is one of the two biggest universities of Switzerland. It's located in French-speaking part in a small town called Lausanne. They say it's a city, but you know, if you compare it to Dnipro city, it's like a town. It's a very nice town, but it's very small. I work there as a doctoral assistant, so basically I'm doing my PhD there right now. And as a doctoral assistant at EPFL, you get to work on cool projects, and this Scala Native thing is a cool project I'm currently working on. That's basically, and today I don't really have that many slides because I'm sort of on vacation, and I was just like Pavel found me like in a coffee shop. I was just chilling there, and he's like, "Do you want to give a talk at the meetup?" And I'm like, "Yeah, it's fine. Yeah, I'll do that." So I don't have that many slides. So please interrupt me and really just interrupt me and ask me questions so that we have a bit more time. So overall, today I would talk about. Okay, does this work? Okay, this works. Today I will talk about this Scala Native thing. I would very briefly tell you what it is, and then how can you use it. And then I was also asked a bit more advanced details how it works. So I will really try not to lose anyone there. So please stop me. Like if you have any question at all, if I'm saying some gibberish nonsense, just stop me. And lastly, I will encourage you to contribute to the project, of course. So what's Scala Native? So Scala Native is a new platform / compiler target / whatever it's a new way to compile Scala code. It's still the same Scala that you know and use. So language is the same. We just added a bit more special magic sauce library to interop with native code, but generally the core language is the same. There are very few, very minor details, but it's essentially just another way to run and compile your Scala code. And it's a compiler, it's an ahead-of-time compiler, meaning that it produces native binaries as C, C++ code would, so it doesn't have a VM, it doesn't have anything, basically like, it doesn't have a million layers of abstractions that stands in between your code and the hardware. That's basically very briefly what it is. And you can read a bit more info on scalanative.org. We don't have that much docs, but bear with me. And now, quick and dirty part. So I'll just give you a very quick intro to how you might want to use it. So basically, it's actually rather simple. So first you do, so all of you use Macs here, right? Yeah? Does anyone use Linux? Okay, good. So basically you do brew install of a few packages. You can find the exact list of packages in this GitHub repo. It basically need to install compilers like LLVM compiler, a few other stuff, but basically just brew install stuff. Then you clone your repo, and then you just say sbt run. And This repo is a very small, a very nice small app in Scala that is compiled with Scala Native. And I will just show you how this essentially will look like. So here I already cloned the repo, and I'm inside it. So this repo is actually a very, very simple thing. So it has a very simple project structure. So it has a build file, it has a fixed Scala versions, and enables this Scala Native plugin. It has a bit more config over here, just it adds plugins and stuff, just a few lines of code really of configuration, and has a simple one-file app, which is actually a ray tracer, so it will produce a pretty image when you run it. So, and Scala Native is built with SBT, so meaning like all of you use SBT here, right? I assume. I mean, if you don't use SBT with Scala, you're having a very hard time. You just don't do that. So that SBT run thing, what it does, it actually does quite a bit of stuff. So it compiles your code, and then it runs it. And the way it does it, I will explain a bit later, but essentially it's a very simple thing from an end-user point of view, because you don't really need to know anything apart from you can run your code with SBT run. And here we just run our ray tracer, and it, what? Okay. It doesn't want to open here. Okay. And it produces this image over here. So it's like a ray traced image. So it just generated some model of 3D scene, and then it like ray traced it to this image. Apparently, it can't open it in preview, but it can preview it in over here. But it doesn't matter. Yeah, Max. Yeah. But essentially, this app is sort of simple. So it has one main. It does a bunch of loops, and it calls this radiance function. This radiance function is the thing that makes ray tracers work. So so to produce a final image, you just iterate over all pixels in the scene, and then you shoot a ray in the direction. And then rays hit stuff, and it might, for example, be refracted, reflected, and so on and so forth. And after it all happens, and you compute the final result, it basically produces the final image. But essentially, simply what it is, it's just a loop over all pixels in a frame, and for each pixel you do a number of samples, and then you call this radiance function. And this radiance function is sort of simple, but and the way you implement it, of course, you use some nice fancy features from Scala Native. So first of all, this first feature is adds structure annotation on classes. So what it does, it turns your class into pass-by-value struct, which does not allocate anything at all. So it just is like a large, nice, fat value, and that's it. So it doesn't, even though we have quite a slow GC at the moment, we are faster on these benchmarks purely because we don't allocate as much. And we do a bunch of structs, and structs can have methods inside them that define a nice operation. Some of them, like for example, you might want to intersect sphere with array and produce a value for it. And you also are able to allocate memory, allocate and touch, and fiddle with direct memory. It's Scala Native. So for example, this malloc here will produce you a pointer of sphere. So it's just like in C. So it's absolutely low-level thing that lets you see the memory as it is. So you can cast and do whatever you want with this pointer, and you can do arbitrary memory stuff on it. So it's essentially a very low-level primitive that is very dangerous, but it is very useful at the same time. Don't overuse it. Yeah, but that's basically what it is. And essentially, the purpose of this small demo was to show how easy it is to compile something with Scala Native. It's basically just a special SBT build with a plugin enabled. And all of the same commands you know and use, like compile and run, are the same. So, and the only other ones that you might also want to use is, so SBT run is the same, so we've just seen that before. The only other command you want that is not standard SBT command is native link. So what it does, it will produce a native binary without running it, because compile doesn't compile to native code, it compiles to intermediate stage. So it's if you ever use Scala JS, no? No, okay. But I'll explain it later. So someone asked for low-level details, so you'll get them. And this native link will also produce this nice binary. So for example, let's say you have this app called My App, and it's in the folder My App, and you will be able to find a nice, absolutely linked and absolutely JVM-free binary inside target Scala 211 My App out. It's a default location. You can customize it in a build if you want to, but essentially this binary thing is just your normal like C-like binary. So it doesn't have any. So it has a few library dependencies on stuff that we use. For example, it has a dependency on GC library and stuff like that. But essentially, it's not too bad. I mean, it's not a JVM that you need to ship like a huge thing. And when you run it, it just runs. It doesn't have any startup time at all, so it just runs immediately because there is no VM. It's already pre-compiled, pre-optimized native code, the same as for C and C++. And if you're a bit more kind of interested into low-level stuff, we'll quickly walk through this other files. So this we also have the NAR files, and you can think of them as Scala Native class files. So basically, they're like intermediate representation that is in between low-level code and high-level code. So somewhere in between, we have this bytecode-like representation, and it's called NAR for Scala Native IR. But it dropped S because it is prettier if it's 3 letters. And then somewhere in between, we have this LVM IR, which is essentially what we give to LVM to compile. You can also fiddle with it and do funny things like people were able to run it on Raspberry Pis, even though we don't officially support Raspberry Pis yet. But because we like LVM is more or less like it's mildly platform dependent, mildly. So if you're lucky, or if we support your platform, it will work. It will just work. Apparently, it just works on latest Raspberry Pi. Yeah, so there is that. And now it's basically nitty-gritty details. Just bear with me. I try to simplify stuff as much as possible, but it's not simple, okay? So essentially, the whole compilation thing from a high-level part where you have Scala code to the final result where you have a final binary is actually quite involved thing. So first of all, we have Scala C or .e over here. So it's a front-end compiler. So it's something that takes source code and produces essentially class files. So the format of class file depends per platform. So for Scala Native, we have NIR. For Scala JS, we have SJS IR. For JVM, we have class files, and so on and so forth. So maybe, so basically, essentially, this part is like somewhere in between what you actually run and what you have in your source code. So Scala C or .e here actually eliminate a lot of features. So the main purpose of a front-end compiler is to remove all of the stuff that is not necessary at runtime. So for example, it type checks everything and will and removes all the fancy features. Then we have this Scala Native part. So it takes NIR of a whole universe. So for example, if you have a large project with many NIR files, it links them together in one like large blob, and then compiles that. Why it does it is because this way we can that code eliminate most code that you don't use. So for example, Scala collections, you don't have to compile all of them every time or like often to produce code if you only use list, right? You only need list and all of the traits that are inherited and so on and so forth. So basically, list and all of its transitive dependencies. And that's basically this part here. So, and then we translate all of that to LVM, and then we give it to LVM, and then we LVM gives it to native linker. And now the same in a bit more detail. So first part is front-end compiler. So the main goal of front-end compiler is to remove all of the high-level features. So for example, stuff like, I don't know, for example, generics. Generics are high-level features which actually in Scala don't exist at runtime, because Scala semantics for generics is erasure, unlike in C++ templates, so it's not the same. But from a runtime point of view, it's a high-level feature because you don't have it at runtime. Runtime doesn't know about generics anymore. It also removes, like, it eliminates pattern matching, it eliminates many, many high-level features. It also additionally actually parses your code. But yeah, it checks your code, it transforms it, and somewhere in the very, very end, once, like, if you use triple dots, it's like a very long list. It's like a very, very long list. It's like 20-something phases, and it's only 20-something phases because in Scala C, phases are fed. In Dotty, I think it's even more. So it's like this list is actually really long. So like, do all of the nice stuff to your code until it looks low-levelish, but you still have classes. So it's not C, C++ code. It has classes, it has GC, and so on and so forth. So and here you get to this code gen part. So code gen translates from one representation to the other. So here we, as an input, we get source code, which is basically bytes of text, right? It's parsed into a tree that is typed. So you get a typed AST, which is also a basis for the acronym tasty. It's a Dotty format for storing type trees, which are still reasonably high level. So it's a new format which will happen in Dotty. But essentially, what it is, it's somewhere after typer, not too much after, just a bit after typer. You take all of this like nice structured representation of your code with types, and you dump it into files. So you have like a very, very high level bytecode, or very, very low level like tree representation. So it's like, it depends on how you look at it. So this typed AST, and then you take this typed AST, iterate over it, and then you produce whatever class file representation that it is for a platform. So for Scala Native, it's NIR. For JVM, it's class files, and for Scala JS, Scala JS IR. All of these IR is actually very different. So for example, Scala Native IR is SSA-based form. So it's I will show you later if you want how it looks like. Okay, good. Then we have Scala JS IR, which is actually a tree-based representation. So it's very, very close. It's not very close, but it's closer to tasty, because it's still a tree-based representation, but it has funny JavaScript semantics features. So it's like a mix of Scala and JavaScript. And then we have JVM bytecode, which is a stack machine. So it operates in terms of push this value on stack, and then like take two values from stack and add them and stuff like that. So it's neither tree nor SSA, it's a stack machine. So, and all three of them are very different. So and basically the question of what gets generated is basically what runs in the end of a compiler, and it's basically backend of the compiler, right? But this backend actually doesn't do much. It just converts from ASTs to whatever representation you need. So the next stage is actually Scala Native compiler, which is basically the interesting part for us. I mean, for me. So the idea here is like, so we have our own IR here, which has all of the features that we wanted to keep. And we want, the first thing we do with that code, eliminate all the stuff as much as possible to produce nice small binaries. And it can even do funny things, like for example, if you use a class but you don't use a method, and nobody overrides this method, and a lot of other invariants hold, this method is not there. So for example, if you have a lot of that code in your code base, it will automatically not see it, because the way linking works, it just starts from the entry point, for example, your main function, and then it just sees that this main function just, what kind of stuff is used in main function? Have I already discovered this? And then it looks through all of the stuff and just does it over and over again until it says, oh, I actually looked over everything, so I know everything I need to know about. But generally, the principle of if tree falls in the forest, it has never fallen here, basically. Then we do some funny things. with it, like we do some optimizations, like for example, we optimize away some boxing operations. We clean up your code to make sure that LLVM likes it afterwards. So we basically, it's not our goal to have some super sophisticated optimizer here, because LLVM is already a super sophisticated optimizer. So what we need is actually to produce code that is easily optimizable by LLVM. So for example, kind of things you need for this is you need to make sure that you don't have too much virtual dispatch, so that you can so that if compiler can remove virtual calls, it should do it, because LLVM is not very good with virtual dispatch. So it tries to make everything as static as possible after the fact. It maps your code to more low-level primitives like structs and pointers. So here, when you emit LLVM, LLVM doesn't have a notion of class or GC. They pretend that they support GC, but it's funny. But essentially, what LLVM IR is, it's SSA form, which I'll show you later, of C-like type system. So it has structs, it has pointers, it has arrays, like C-like arrays, but it doesn't know anything about high-level features like classes or GC. There is some very, very minor support for GC, but it's essentially not there. And so next step is LLVM. So LLVM is actually a very, very nice optimizer for C and C++. It's like state-of-the-art. It's basically on par with GCC for most benchmarks. I mean, it's sometimes slower. When I say sometimes slower, it's like 5% slower than GCC. It's basically like non-existent. And sometimes it produces bigger code and stuff. So GCC is often better, but by tiny margin. And the nice thing about LLVM compared to GCC is that it actually has a programmable API that is exposed to you as a software developer. For example, Scala Native is only possible because this LLVM intermediate representation is actually very well specified and documented. And it would not be possible, for example, to do the same thing with GCC, because GCC does not provide you any guarantees on its internal equivalent of this, because it essentially is just an implementation detail. So GCC guys want you to generate C code, but this has its own issues. They made a lot of effort to make it work, like generate C code and then preserving all of the debug information and so on and so forth. But still, it's not very it's not as friendly as LLVM IR, because LLVM IR is like a stable format that has a very clear evolution kind of policy of deprecating kind of structures and features and adding new features, and it's actually rather nice. And they also have this huge optimizer coupled with the IR, which is nice. So idea of LLVM is basically to have low-level enough representation that is still high-level enough to do optimizations that they want. So and when I mean they want, I mean C, C++. So it's actually very good at this, and it's not very good at some other features. But as long as we produce code that looks like C and C++, LLVM will happily optimize everything away. So it will unroll loops, it will do everything it can to make a nice, fast final binary. And speaking in terms of representations, so I was trying to highlight kind of what's going on. So basically, this one operates on LLVM IR. So we've had typed AST, NIR, and now LLVM IR. And now, lastly, this should be S, but okay. And lastly, LLVM basically produces assembly code, essentially, I mean, in a simplified way. And an assembly code is assembled into object file, which is essentially machine code with some minor information unspecified. Like, for example, if you have functions, it doesn't know where this function is. So you need a linker, another linker, to link all these files into one actual machine code file. But essentially, all this stuff is kind of happens under the hood. But basically, this is kind of the pipeline that goes on. So it's actually like very, very many different representations that kind of like, and all have a very good reason to exist. So we start with Scala code, which is a nice high-level language that you actually write, right? And then it produces typed ASTs. You would not want to write typed ASTs by hand, trust me. And then it produces NIR, and then like every single step of the way, it's lower and lower levels. For example, even LLVM has two representations inside. It has LLVM IR and has something called machine instruction, which is a representation that knows about hardware. So for example, at some point LLVM says, I've optimized everything in a platform-independent way as much as I could, and now I really need information about what kind of hardware are we going, what kind of hardware code we need to produce, because for example, register allocation, like SSA doesn't have normal x86 like registers. It has infinitely many named registers, but it's not what happens in real life. So you need to map one to another. So you need some kind of representation to kind of just stand in between, because if you would produce native object files straight away, it would be a bit hard. And then you have native object files, which is still not cooked enough. I mean, it's basically like a slow process of cooking your code. And then finally, in the end, you get a nice binary. Okay. Okay, so, and now just a quick demo of what it looks like. So here you have this thing called HNIR, which is a human readable NIR, and then you have this other one, which is a binary. That's the one that compiler uses, and it's the one that you should use. And here you have basically, let's take some functions side by side to kind of to make it clear what's going on. So. Okay. So we have main here, right, somewhere. Essentially, this main function and this main function are the same, only that the one on top is SSA form. So what it means is that instead of having expressions and all those nice high-level Scala-like features, what you have instead is a very flat structure. And this flat structure has essentially a two-level nesting only. So it cannot go more than two levels. So it has something called basic blocks, which are like local pieces in your code that you can jump to. And you can also, when you jump, you can pass values as parameters. So for example, the first block is the entry block. So there's a block that you jump to when you call a function. So when you call a function, if you look at the signature over here, so it's a function that takes demo main and object array, which represent args over here, and it produces nothing. And here we have the same thing, right? But the only difference is that here you in blocks unlike functions cannot really return values. They can only jump to other blocks or return from other functions. Essentially, if you only use local functions in tail call position, that's kind of similar to what basic blocks are, kind of similar. And this structure here has a very flat thing of basically name equals instruction. And instruction is essentially just opcode and a bunch of values that you take. So for example, here we produce new array, right? And new array takes two vectors. The first vector is basically here. Wait, no. Here's the first one. So here is our first vector. Oh, actually, no. I was right. So the first vector is basically, so how you produce a struct. So first you take something called undefined, which is undefined value of some type. So it's a struct, an instance of a vector where all three fields are unknown. And then you insert fields. So basically you explicitly update fields in like in a functional style. But you do it one field at a time because you really kind of need to make sure that every instruction is as simple as possible. So there's a goal of SSA. So you don't want complicated instructions. You want simple, very simple instructions which compose well. And then to make a large expression like new array of new vec, you create a bigger sequence of instructions that do the same thing. a nice benefit of having this flat structure is essentially it's very, very normalizing, is that there are many different source code forms mapped to the same IR forms. For example, if we move this vector here to local value here, vec1, and this one to the other one, and then recompile, we'll actually get the same IR. Clean compile. See, basically, even though we changed code, even though we changed code, it did not update yet. Sorry. Vim, yeah. So even though we changed the code, the SSA form is the same. That's basically the beauty of SSA, is that it essentially normalizes the code to some kind of common denominator that's easy to optimize, because many different source code forms have the same SSA form. If you do an optimization on SSA, it's easier to target wider spectrum of code. So for example, if you would optimize, if you would write an optimizer on trees as opposed to an optimizer on SSA, we would need to account for all the possible ways to do the same thing. So for example, from tree point of view, the tree we had before and the new one are completely different, because now you have more statements, now you have values. In Scala C, values have symbols, they have types, they have lots of information that you carry around, and you will need to work a lot harder to do the same thing, basically. And this is kind of the main beauty of SSA, is that it makes it easier to optimize wildly different code into kind of a simpler, normalized form. And its language, this NAR language is like a small intermediate language, which is actually a bit documented even. So we have an issue, document internals, and there you actually have a comment with work in progress docs for this. So if you're interested in how it works a bit more, so you can check it out. And then, keeping this open, we will open LVMIR. Okay. Come on. Okay. I cleaned everything up. Here we have LVMIR. So here we have main somewhere. And here it's the same thing, but the same thing as before, but lower level, way lower level. So, for example, you don't have classes anymore, you still have structs. But for example, you really kind of have a very low-level type system that is actually C++ like. But in a sense, it's very, very close, because many features overlap. So for example, arithmetics and functions and function calls are almost the same. But still, there are some differences. And the main goal of NAR in this kind of whole thing is to have a nice analyzable representation that still preserves high-level features we want. We actually want the least amount of high-level features. If we could compile straight to LLVM with the same functionality, we would do that. But to do this kind of that code elimination, we actually need to have a representation to analyze, because otherwise LVMIR is already too lossy for example, to remember. It would be way too hard to remember what is the class and how it's compiled to LLVM and analyze LLVMIR, which we produce. And it's actually way easier to have your own representation as you can play with. It's basically a very, very brief intro into how it works. So, and lastly, I would like to encourage all of you to contribute. We have 19 guys, as far as now, it's just guys, yeah. Working on the project, we have lots of issues closed, lots of PRs closed. We are quickly charging forwards to 0.1. We are already usable as a 0.1 snapshot, so you can already clone it and play with it without having to build everything from scratch. So it's nice. So basically, we have lots of nice things you can contribute if you want to. For example, you can improve the docs. That would be really nice. Huh? And we have this nice, cozy, friendly chat that you should definitely visit. And just if you have any questions at all, as you forgot to ask now and you want to ask later, just go there. Yeah. So this one is actually kind of famous. So people like are kind of interested in making it work in some weird places. So some guy contributed FreeBSD support. Some other guy made it, or either made it work or just works on Raspberry Pi, like the latest Raspberry Pi, and so on and so forth. So, do you have any questions? Yeah.
Reflection codes. Is this stuff can compile reflection codes or?
So, reflection storage is kind of complicated. The main reason why Scala.js doesn't support it is because this nice part of removing all the codes that you don't need. We are doing it because it's nice, but it would still work if it would produce like tens of megabytes of binaries, right? Like our binaries are quite small right now, but it would still work as a product if it would produce fat binaries. But for Scala.js, it's absolutely impossible to produce fat binaries because like you load it every time you visit a web page, and you cannot possibly expect people to use a compiler to JavaScript that makes you download like 20 megabytes of Scala standard library. So essentially, for Scala.js, it's absolutely crucial to have the best dead code eliminations they can possibly have. So they spent all of the effort there, and reflection doesn't really interact well with that because, so let's say you do something like class for name. So it means you can at runtime decide a string that will require a VM on JVM to load a class, which could have potentially been not reachable before, right? So on Scala.js, it's basically hard to impossible to implement it. On native, it's possible, but most likely, so we have some plans to have slightly more wide support for reflection with Scala.js, but you will have to pay for it in terms of you will have more code compiled. Basically, your binaries will be bigger and so on and so forth. And one restriction that we also have is similar to Scala.js is that you cannot load code that was not there. So for example, if you do class for name of the class which was not there at all before, and you will have to somehow inform the compiler that you want this class, because the way this compilation works, it compiles stuff ahead of time. So it cannot just at runtime see, oh, you did class for names, class I didn't see before, so I will just recompile everything. That's basically what JVM does under the hood. And this is one of the reasons why JVM startup time is slow, because every time you do reflective class loading, it can invalidate already compiled code, which actually makes it worse. So for us, startup time is one of the top priorities, so we don't really want to have a JIT, so we want to have an ahead-of-time compiler. So we'll probably most likely never have dynamic code loading, so we will not be able to load new bytecode or anything like that. But we plan to support reflecting on a code that you do have. So for example, if you have, after all of that code elimination, you have a nice classes left, like you actually use, you'll be able to look at their structure, you'll be able to see what fields they have, and so on and so forth. But exact interaction with that code elimination is complicated, and for Scala.js, it's absolutely understandable why they decided not support it.
Okay, thank you. And one more question.
Yeah.
For example, is it reasonable to compile with Scala Native my web application, for example, on Play or Akka?
So Akka, so basically the question is, do you have all of the alternative libraries implemented in Scala? So for example, for Akka, as far as I know, they've been moving towards to having everything implemented in Scala for a while now. So, and as far as I know, Akka runs on JavaScript now, so there's this project called Akka.js. Yeah. So basically, it's Scala.js port of Akka. So if it can be made work on Scala.js, it will most definitely will be able to make it work on Scala Native, because we can do more. But the thing is, it will take some time until we get all of the necessary, like basically transitive closure of libraries supported. For Akka, actually, I'm quite hopeful. For something like Play, as far as now, Play still in some configuration uses Java HTTP frameworks and stuff like that. Is it true? Yeah. So basically, as soon as you use something apart from Java IO, NIO, Net, Lang, and util, basically like core libraries. Like if you use something like servlets, we will not support servlets. But for example, Akka HTTP is, as far as I know, is done from scratch. So it would be great to support Akka HTTP. So I'm looking forward to that.
No one else wants. From which it started? I mean, from what point you decided to go for the Scala Native? Like, what was the initial reason to try? I mean, just for fun?
So basically, the reason why Scala Native exists is because I'm really seriously annoyed with the JVM. You know, it's true. It's like it's a real story. I was annoyed with JVM for a while, and I bugged Martin for a few years about this thing, and then he finally gave up and said, like, you can try it. and so far it's going reasonably well, I would say. So we have lots of interest from the community. We have contributors. We have so the project is just 1 year old. So yeah, basically so far so good.
Do you have metaprogramming support as of now?
So you can always use something like macros, macro annotations and stuff like that, because it happens before Scala Native happens. So
they are supported from the compiler, right?
Yeah. So Scala C supports.
Okay.
So basically, if you use Scala C, you will have macros.
Another question: do you have any FFI support?
Yes.
Yeah, okay.
So we have a very, very easy to use FFI thing. I will just quickly show how it looks like. It's actually way simpler than GNI, and I really hate GNI. Another thing that I really hate, yeah. So here is all you need to do. So to call a C function that takes a pointer and returns a double, that's all you need to do. You define a signature, and you say it's somewhere there in C world. It's extern. So it's similar to how C++ extern works. You have this extern object block, and you have this extern field and extern declarations. And whenever you call them, it will automatically wire them to corresponding C function. So there is like nothing else. So all you need to do is you need to have you need to pass C flags to find this library. Like so, this one is standard function. But for example, if you use some C library, you will also be able to say link foo, and it will automatically link with library foo, which basically libfoo dot so, for example. Yeah. And essentially that's all you need. So you need to know the name of the library, and you need to know how the signature looks like. That's it. And you need to type the signature. That's it. It's basically as complicated as it is. Yeah.
Now you hear me? Oh, now it's good. The question about the roadmap, for instance, I wish to see it be a production ready. I mean, like without any. Yeah.
Okay. So basically,
What's the way?
I will not give you any dates. So right now, our next goal is 0.1. That's basically not 1.0, but 0.1. So by 0.1, we want to have essentially it's been usable for a while. We have some minor stuff missing, like we need a bit more SBD integration for packaging and publishing artifacts. A contributor is working on that, so it actually might happen sooner than you think. But from there, our idea is to release often and essentially have a tight feedback loop with people who use it. So essentially, if you want to make it more stable, faster, you'll, as soon as we release 0.1, try it, and if it doesn't work for you, complain. And if you do it enough times, it's stable, basically. Yeah.
Okay, who participate the most? I mean, what the background you need to do to participate?
So to contribute, you really need just like if you know Scala, that's all you need basically. So we have some very simple stuff that you might would contribute. Like for example, one of the large pieces of work that we are don't sleep. One of the large pieces of work that is still in progress is that all of this Java IO and IO lang and stuff is needs to be implemented. But when I say needs to be implemented, it's more like needs to be ported from Apache Harmony. So our current strategy is to either port from Apache Harmony or implement stuff from scratch. We cannot look at JDK source code because that's GPL and we are Scala licensed. So essentially for licensing reasons and for reasons of Oracle potentially being angry at us, we do not look at any of the JDK source code and should neither any of the contributors of the project. So if you want to contribute, you should never look at the source code of JDK. Yeah, it's basically our official rules for accepting contributions. Essentially, the work necessary is just improve coverage of JDK libraries. Is essentially, it's an infinite amount of work, but we don't need to implement all of it. We only need part that we need, right? So for example, if somebody needs this particular function, we add it. If nobody takes about this weird overload or this weird specific kind of Java-like thing that nobody actually touches in practice, we would not implement it, basically. And given this kind of constraint, it's very doable to implement libraries that people actually want. But actually, there is lots of simple work there. Basically, we already have a reference implementation in Java very often, and we just port that to Scala. And it's essentially minor code changes, basically the same code. Sometimes you need to be creative around the fact that in Java code is a bit different, like with loops and stuff, but it's really minor changes. So essentially, very often we just port existing parts of libraries as is with minor. And you don't really need any experience there. So you just come to the chat and ask, I want to port some JDK stuff, like what should I do? And we have like lots of work there, and it needs no experience whatsoever. Just a basic knowledge of Scala and Java, I think, would do. And for compiler work, if you're interested in that, you will probably need a bit more background. But again, like if you have any questions at all, and if you want to figure something out but it's not clear, you just go to the chat room and just say this is not clear, and it will help you. Basically, that's how it works. If enough people complain about something not clear, maybe we'll finally have some docs. Yeah.
Is there anything specific using Scala Native on Linux?
So right now, I think we
Use Mac.
We are fine with so our CI works on Debian, I think. So on Debian and Mac, it definitely works on Linux. It works in our CI. We don't test with every possible distribution and stuff. We don't know every possible package name for every possible distro, but if you use Debian Ubuntu, it should be very easy because we actually have it in CI. You can just copy paste the stuff, and it just works on Linux. Sometimes you need to install packages which are named differently because every single package manager has everything named differently. Yeah, essentially Linux and Mac x86, 64 is our kind of main platforms right now. Everything else might or might not work, kind of, no guarantee. But this one are in the CI, so basically results are good.
I have another question. Is the Scala Native compiler written in Scala Native?
It's written in Scala, which is by default.
It requires JDK, right?
To build your code, yes. So right now, to build your code, you need JDK. So our build infrastructure runs on JVM right now.
Do you have plans to bootstrap your?
Hopefully, eventually, but this essentially not a blocker because it's so once we have better support for I/O in the Scala Native itself, we'll be able to use the same code to compile it to native code. And we have some people interested in alternative build tools like CBT, which is actually possible to bootstrap on native, unlike SBT, which is a huge monster. But it's nice. Just use SBT. Everything else is worse.
Could you say a few words about the memory model in the Scala Native?
So normal classes like class C, new C, are GC managed, just like on JVM. We don't have a specified memory model for concurrency and parallelism stuff. So we don't yet have anything like Java memory model yet. But we are garbage collected and essentially our goal is to have main Scala language unchanged. We don't want to have any semantic differences with main Scala. And then we have this pointer of T-type, which is kind of a nice backdoor into native world where everything is possible. So that one you can do whatever you want. So you can manage memory yourself. You can use funny native memory managers, like you can use memory pools and stuff like that. So it's very low-level thing, and it has essentially the same kind of performance and implications as C pointers. So it's basically no safety and no overhead. So basically, if you want that, you can use pointers directly, and you will get like. But the main purpose of pointers is to first have a nice interrupt story, so that you can just write signatures in externs as it is in C code. So if you have pointer to int, you will just write it as pointer to int. Okay, you don't need to invent stuff like with GNI. And it's very easy because basically you get the same pointer, and it's the same pointer, and behaves on Scala side in the same way as it does on C side. So you don't need any glue code like with GNI.
One more question.
Yeah.
How close your implementation of pointers, for example, to C pointers, when I can just call memory by address and interact with it? Like, for example, if I do embedded solution, is it the same, or I have some restrictions?
You can do whatever you want. That's the whole point. Like with pointers, you can do whatever you want, but it's unsafe. Basically, it's pointers.
Just a question with comparison with other like growing languages. Let's take as an example the Rust.
Okay.
I understand if we will like get rid of all the concurrency parallelism stuff. What's the it's still the huge question. Yes, some benchmarks.
Benchmarks. We don't have any benchmarks that we would claim as in like reproducible benchmarks. So until we do that, we don't want to name any performance numbers. But that completely unscientific one is essentially around I think 30 or 40% slower than C++, and Rust should be around similar. And essentially because we don't optimize one of the Scala features yet. So we don't optimize this in Scala. Top-level objects have a bit funny semantics because they're lazily initialized. So for example, if you have side effects in them, it needs to preserve side effects in terms of lazy loading. And this is why when you call a similarly top-level function in a companion, it is not exactly the same as C call yet. But we plan to optimize it away. So basically, as far as I know, that's the main blocker. And once it's done, essentially you're always like, as soon as you only use low-level features like pointers and structs and objects, basically if you write low-level code, you'll get low-level code performance. High-level code is probably slower. I cannot say by how, but it's our goal to have low-level code, basically C-like code, be as fast as C, because that's not impossible. Essentially, as soon as you write C code in Scala syntax, it should compile and have the same performance as C code in Scala syntax.
Question about how to just due I don't have that experience. For instance, you develop now this Scala Native compiler, and from where the requests for some features not working or we need this feature comes from? Just like seeing the JDK stuff?
So mostly right now, most of the stuff that is broken is because of the JDK. So for example, somebody tries to call something and it depends on part of the JDK that we don't have, or it's re-implemented or we implement it imperfectly, and then it's a bug. But most of the time it's that. So we have not had any major, like we have one major bug about exceptions right now, but we have fixed two. So essentially, it's like the issues we have right now are mostly we don't have enough of JDK supported yet. And there is still some work to be done to make it nicer. So for example, right now we don't print stack trace by default, so you need to run it from LDB, from within LDB to see a stack trace, but it's not really that big of a deal at the moment, considering the version number, like 0.1 snapshot. Over time, everything will be way nicer. So for debugging of the applications in Scala Native, you're already able to use LDB. So right now it will show you assembly code, which is not completely nice. But you already are able to debug assembly code, which is not too bad. And in the future, you'll also see source position, so it will basically be able to show you original source code. So basically, for example, if it crashed here, because if you did something crazy with pointers, it will show you that it crashed right there. So it will definitely know the correlation between source code and runtime.
What about debugging, or
What about what?
debug for how the compiler works?
Debugging of the compiler is complicated. So basically, you should normally not have to do this. But in the worst case, basically you are already able to observe all of the steps in the compilation. So so right now we have this many-phase design of the compiler, where after every phase you can print the whole thing and see basically what compiler did. But we are slowly moving forwards towards a single pass compiler for performance reasons. But still, like, it's not impossible. Just you need to understand LVMIR and Scala Native IR. It's basically like, as soon as you understand those two, you can definitely understand what compiler does to your code and where it does it. And the compiler itself is actually quite small, and it's our goal to keep it small. So we don't want code. Code is bad.
The GC now comes from the LLVM, right?
So GC comes from something called Boehm GC, which is a C++ GC. We are thinking of replacing that with something called Apache OMR. It's better GC that we can also use on Scala Native. And maybe we'll also experiment with a GC of our own. Basically, right now, GC is not an issue. It's an issue of having enough libraries implemented and an issue of having nice tools and basic documentation, stuff like that. So once we get to performance being a problem somewhere, we'll start focusing on that, but we are not there yet. So okay, good. Thanks.
Thank you.